Afternoon, Pete. God. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma rays. Who picked those 7? If you had to pick an odd one out, which one would it be? Obviously, there's only one that can be seen, isn't there? There's only one that can be seen. So why is it in there? What we can see have to do with radio waves, isn't it? Waves. That's how far we've had to dig. Who decided that should go in with radio waves, and ultraviolet, and X-rays, gamma rays, infrared? I'm being serious. What has it got in common with the stuff that we can't see? Dodgy day today, but you can always count on something, can't we? So who decided that this should go in with all of the stuff that you can't see? Where is the logic, seriously, in that? Oh, what's he saying now? Well, what do you think I'm saying? I know that it does not take at the start 8 minutes and 20 seconds to radiate Mickey Mouse photons to here. Its light is absolute. There is no sign anywhere, and it's highly illogical to think that it takes 4.6 seconds for that sun, for that star, to radiate light the distance of its diameter. Nothing takes 4.6 seconds to radiate light the distance of its diameter. Who picked the 7? Why was it put in with this? Doesn't really make sense, does it? I think we nearly missed it. Obviously a reaction between moisture and glass. Water, moisture, always the same angle. It has to be at a certain angle. Constant, isn't it? Right, so last night I immersed myself in it, and I found a lady, and she was talking about the stuff, right? I'm not going to say a name, but let's listen first. Some of you in the US might know her. I've never heard of her, but I was all in about the colour. I was all in. I was up all night listening to things, and this grabbed me. It's 23 minutes, this one, but we're only going to listen to a couple of minutes, and then I'll tell you why we're only going to listen to a couple of minutes. All right, colour vision, rod and cone cells in the retina. Now this lady is about to explain why the sky is blue.
Okay, so there's a related question here, which is a question that seems like a philosophical question at some point. Why is the sky blue? Well, why is the sky blue? This actually has a really interesting set of explanations that combines some explanations from physics, but also has a little bit to do with what we just learned about human visual perception. So, as you all know, the light from the sun is not blue, right? If you just look at the spectrum of the sun, it pretty much spans the entire visible spectrum. And so if you add all of those different colors of light together, the perception of that type of light is usually white. So why is it that when you look at the sky, it doesn't look white? It looks blue instead. So this is something that my kids asked me at some point, and so I actually figured it out. And so here's kind of the short explanation of why the sky is blue. The first thing we have to understand is this thing called Rayleigh scattering. So the atmosphere is filled out of gaseous molecules, most of it's nitrogen and oxygen, okay? These are teeny tiny little gas molecules. And so because they're so small, for that size of gas particle sizes, when light comes down from the sun and hits the atmosphere, the probability that it will hit one of these particles and scatter is not uniform with respect to wavelength. Longer wavelengths of light are less likely to be scattered. They're more likely to just pass right through, whereas shorter wavelengths of light are much more likely to hit one of these gas molecules and be bounced around and change directions. Let's think about this for a second. If you are a red light photon, you are much more likely to go directly down. But if you are a blue or a purple photon, you are more likely to be bouncing around the atmosphere and end up going sideways. The consequence of this is that because you're standing on Earth, and you're normally not looking straight up at the sun. In case nobody's told you, don't do that. It's not a good idea. Don't look straight up at the sun. So when we look at the sky and we perceive the color of the sky, mostly we're looking at the sun.
I only just picked up on this one. I've watched it twice, from start to end, twice. She's saying if you're a red photon, you travel straight down or something. But they're just photons, aren't they? Don't they have to reach where they're going and then decide what the surface is to decide the wavelength? So what was that?
Eyes, right? We're not looking at the sun. We're looking at the sun like reflected by the atmosphere, so that it's now coming from the side rather than coming from the top. And those photons have to have bounced quite a bit. They arrived at my eye sideways. So they must have bounced around quite a bit in the atmosphere before they started going sideways and hit my eye when I'm sitting or standing on Earth. And because the Rayleigh scattering is so severe, the likelihood of the scattering is actually proportional to 1 over the wavelength to the 4th power. So these shorter wavelengths of light are significantly more likely to be scattered and going sideways. Okay? So that's why the spectrum of the sky, the perceived color of the sky, is much more skewed towards the blue, violet, purple side of the spectrum than towards the red and orange side of the spectrum. Now, the sunset is a different thing. That has a different type of scattering. That's not really scattering. We talk about it a different day if you want to, but this is what happens at noon, not when we're talking about the sunset. That's why this is when you look at a cloudless, clear sky, to most of us, we perceive it as being blue. But this explanation is actually so incomplete, because this explains why the sky is lighter in color towards the shorter wavelengths part of the spectrum. It doesn't explain why it's blue instead of violet. To understand why humans perceive it as being blue instead of violet, we have to also look at the absorption spectrum of the short wavelength photoreceptor color.
Now, I watched this, honestly, all the way through, from start to finish. And by the end of it, I was like, right, this is BS, all of it, right? Exited, and then there was more of her. So then, because that, you cannot tell me that was convincing, right? But then listen, I went, hang on a minute, saw these other ones, so I thought, right, let me just jump into, which one was it? I can't remember. Type neurotransmitters, whatever, right? Let's go, actual properties and neurotransmitters, go away, honestly, oh, here we go, intro to neuroscience, the first one. Listen.
Let's talk about brains. Hi, my name is Bing Breton, and I'm a neuroscientist at the University of Washington in Seattle. In this video, I'm going to introduce to you the next series of videos that comprise a university-level course on Introduction to Neuroscience. This is a course that I've taught several times at University of Washington, and so I'm going to talk to you about the topics that we're going to cover, as well as my expectations and hopes for you. of your metabolic costs. So about 20% of the calories you're burning at any particular moment when you're not doing anything, this is not true if you're running a marathon, is devoted to just keeping the brain alive and functioning and ready to do the next thing that it's getting ready to do. So that's one indication of how important it is. Now, a few more things about the brain that I think are really interesting, just that I like thinking about size scales and time scales. The brain, hopefully the careers of lots of other people in the world as well. So from my perspective, one of the coolest things about neuroscience is that the brain has multi-scale structures in space. Now I'm going to break that down and tell you what I mean by that phrase. What we're looking at here...
When I started to listen to these, I ended up watching 3 or 4 of them. Seriously, right? She knows her shit. Right? She does. I'm not just saying.
Actually, we have power plants, we have recycling plants even. This is very green here. And that is only one synapse among all of the synapses that...
she's on it. She knows. She doesn't need to check anything, right? She is on the ball.
Visual creatures. And so...
Hang on. My point is...
Welcome back to Introduction to Neuroscience, where we're going to get started at the beginning. This is the ABCs of neuroscience.
Last 30
and we're going
seconds.
to be talking about...
Right? Just anywhere, random.
And the one that I have in my clicker right here, that would be a 300,000 volt battery. So this is quite a bit of charge that's being maintained across the plasma membrane, across the lipid bilayer membrane that is the cellular membrane.
She's just on the ball.
Additionally, most neurons are highly permeable to potassium at rest. Now, I told you before that cell membranes are impermeable to ions, and that's true, okay? The trick here is that the reason the cells do this is because they actually are then able to express proteins
half an hour
and control.
She knows her stuff. And then I noticed all of these 2 years ago, 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 all of them, until we get to visual perception, retina, photoreceptors, neurospin. And it is the only one, colour vision, running clone cells in the retina. Now,
a cloudless, clear sky, to most of us, we perceive it as being blue. But this explanation is actually still incomplete, because this explains why the sky is lighter in color towards the shorter wavelengths part of the spectrum. It doesn't explain why it's blue instead of violet. To understand why humans perceive it as being blue instead of violet, we have to also look at the absorption spectrum of the short wavelength photoreceptor cones in our
it's not her thing. She was asked to do this.
You can see here that the peak absorption spectrum,
right? That sky blue thing, if you're a red photon coming down, the reason I keep at this, right, is because I know for a fact, I know that the sun's light is absolute. And all of these things have holes in them. Again, why is the visible spectrum in with 6 of those that you can't even see? What have they got to do with the visible spectrum? They're all invisible. So straight away, that does not belong there. Secondly, if the sun's light is absolute, it does not get processed in the back of the retinas. We see things of colour where they are. I'm looking at red books, blue books, dark green books. It's not photons come sideways at me. I see stuff. I don't have to wait for stuff to come to me. My eyes go to it. The more I think about this, the more certain I am that they've just asked her to, because she's a good talker, but it wasn't convincing. So, I'm going nowhere. I guarantee you, the sun's light is absolute. I will answer some messages today. I've been flat out. It's only one me. All right, peeps. I'm telling you that who came up with those right in the middle. Yeah, right. Later, peeps.